Hi everybody, and welcome back to our data structures and algorithm series. In this video, we are going to learn about stacks. We're going to learn what stacks are, how they work, and then after we understand that, we are going to implement a stack. So let's get started. So what is a stack? A stack is a restricted access linear data structure. It can only be accessed at one of its ends, and that's how you add and remove from it. A classic analogy of this is like a stack of trays at a cafeteria. The trays at the cafeteria are removed from the top and they're placed back at the top. So basically, the first tray that's placed in the pile would end up being the last one taken because trays keep going on top. And when you start taking the trays, you take it from the top. So the first tray in that pile is the last one removed. So in this case, a stack is therefore known as a last in and first out structure, or LIFO. Stacks are particularly useful in situations where data has to be stored and processed in a reverse order because of this structure. Stacks are particularly useful in situations where data has to be stored and processed in a reverse order. And there's many applications that do this. For example, if you need to evaluate expressions and parse syntax, you would use a stack. A compiler, which looks at balancing delimiters in program code, would use a stack. And this is really important because no program is considered correct if the delimiters are mismatched. Another example is converting numbers between bases, processing financial data, and then backtracking algorithms. So now we've gotten a high-level overview of a stack. Let's look at the operations that we can perform on a stack. And I'm going to do this by visualizing a stack and talking about the different methods that we can perform. So what I'm going to do is walk through the different operations that we can perform on a stack. And the first thing I'm going to do is draw our stack. And our stack is empty. The best way to visualize a stack is kind of like a bucket. So this is a common way that people draw out stacks. It's like an empty bucket because when we place items in, it's going to go to the bottom. And it's a very easy way to visualize that last in, first out method. So there are several operations that we can perform on a stack. One operation is clear, and you can think of clear as the fact that we clear a stack. Another operation is empty, and this checks if our stack is empty. In the case right now where our stack is in, it is empty. So if we said is empty, this would return true. Another is push, and this pushes a specific element. So I'm going to write EL for element. This pushes that specific data item or element onto the top of the stack. Now, when we want to remove an item from the top of the stack, we do a method called pop. And pop removes the top element from the stack. There's another method where if we could just look at the top element of the stack, but not remove it. And that method would be sometimes called peek, sometimes it's called top. So we're just going to call it peek so we can have a little bit of alliteration here with all of our P's. So this is just going to look at what is the top element in the stack, not remove it. So let's walk through what happens when we push and pop from our stack. So we have an empty stack here. It would return is empty of true. So let's say we push 5 to our stack. Then our stack would become 5. 5 is added to our stack. At this moment, if we called peek, it would return 5 because 5 is the top element in our stack and it's the only element in our stack. If we call push 10, Now our stack becomes 5, right? That's already there in our stack, and 10 is added to the stack. So now when we call peak, 10 is the top element in our stack. It's no longer 5. So 10 is the top element in our stack. If we called pop, then 10 would be removed from our stack, and therefore our stack goes back to 5. 10 has been removed from our stack. So now that you've gotten a high-level overview of a stack and the operations that are done on a stack, let's implement a stack. I'm going to show you multiple ways on how to implement a stack. I'm going to show you how to implement a stack using a list, which we've already learned from before. And I'm also going to show you how to implement a stack using vectors. So first, let's learn how to implement a stack using a list. And we're actually going to use the list in the C++ library instead of using the list that we have implemented. Because again, this is the point that we're going to learn how to implement these things. But going forward, there's no reason to implement a stack on your own. It's already been done. You can use the standard template library in C++, which has common data structures that we're going to learn about. But again, you need to understand how these data structures work so that you can understand the inefficiencies and efficiencies in using those structures. So I have a new folder here called stacks, and inside this folder, I'm going to make the file called stacklist.cpp. And what we're going to create is a simple C++ program that uses the list from the standard template library that's available in C++ to implement a stack. So the first thing we're going to do is, for simplicity's sake, we are going to define the class in this program, and then we're also going to have a main method within this file, because this can all just be done in one file. So first I'm going to do if not define, I'm going to define stack, and then we're going to do an end if. So our class definition is going in here. This is where our definition of a stack will be. And after we finish writing up this class, we will then make the main method below the end if. So as I mentioned before, we're going to use the list from the standard template library in C++. So we're going to include list. And then for sanity's sake, we're going to do using namespace std, just to save us some headaches from having to always include std for everything. So now we are going to define our class stack. List from the standard template library is similar to how we created our linked list in the last video, and that means it is a template class. So the same idea with our stacks, we want our stacks to also be a template so that we can change the type as needed dynamically. So we will define it as a template class T, and then define the class, and this will be class stack. So now our class is going to have some private attributes and some public attributes. So our private attribute, the one thing that we don't want any class or function outside of this class to be able to access, is the list that is the underlying part of our stack. So this is where we call list T. This is calling the standard template library's list, and this happens to be a doubly linked list in C++. So we're going to use the list, and we'll call it LST. So this list, we don't want anybody to be able to access, and because of that, we put it behind private. This is encapsulation, one of the fundamentals of object-oriented programming. So we are encapsulating it so that no other classes that have access to stack can modify it. So now we're going to add our public methods, and these are the methods that are going to be accessed publicly when you initiate a stack. So our first one is our constructor. So that will just be an empty constructor called stack. And then we have the methods that we defined earlier when I drew out the operations that a stack does. So let me open that to the side. So the methods that we are going to define are clear, which empties our stack, is empty, that lets us know whether or not our stack is empty, push, which adds an element to the top of our stack, pop, which removes an element from the top of our stack, and peek, which just looks at the top element in our stack. So first, let's define clear. So clear returns nothing, so it's a void method. So it'll be void clear, and we'll actually call the method for the list that clears. So we use list.clear. List.clear. This erases all the elements in the list, and just like with a doubly linked list, it's going to iterate through and clear out each element. Then we are going to implement the function isEmpty. IsEmpty returns a boolean. It's 1 or 0, and it's actually a constant. So we're going to write bool isEmpty, and this is a const, and this is the type that is actually returned by the list method for our standard template library. So we're going to return lst.empty. This returns a boolean, a constant boolean, and it returns true only if the list is empty. So now let's implement our push. Now, if you remember, our stack is going to be represented by a list. So when we push to our stack, which means that we add it on top of our stack, let's take our stack, put it to the side, and we're adding it to the back of our list. So void push, and we're going to take a reference to an element, lst dot push back. Pushback is a method that's available from our standard template library, and it just adds the element to the end of our list. If you look at push front, same thing, except it's adding it to the front of the list. Push back, yeah. And I saved, and I have a little auto formatter, so it's actually auto formatting when I save to make sure that I actually keep things formatted nicely. Our next is pop. Pop is going to return the element that is at the top of our stack. In this case, the top of our stack is, the last element in our list. So we're going to have to remove the last element from our list and also return the data with it. So T is our type, pop. So we're going to store the last element in our list. So list.back, this is getting the last element in the list. And then we use lst dot the pop back method, which will remove the last element from the list. The pop back method doesn't return anything, it is void. And since we want to return an element for our pop, we want to receive back 5, that's why we have to access the last element first before popping the last element, i.e. removing the last element. So we stored the last element, then we removed the last element. Now we need to return that element. So we write return EL. All right, now let's implement the last method, and that is peek. Peek is going to return a reference to the last element in the list. So we can just do reference of this element, and we would return lst dot back. So now we've implemented our stack using the list from our STL. Let's test this implementation. So I'm going to just bring over some test code, and it's actually going to be mocking what we've done here with pushing 5, pushing 10, and then popping. So I'm going to add it after our end if. So I'm going to add it right after our end if. And this uses cout, so I'm going to also include iostream. So going back to the test code that I have here, this is initiating a stack that's using integer as its its type. The first test we're doing is checking if the stack is empty. So here we've initiated our stack, and when we check here, our stack is empty, there's nothing in it. This will return 1. Then we are going to push 5, just like in our example. Our stack is no longer empty. So when we check if it's empty, we should get 0 returned for false. If we peek at the top of our stack, the top of our stack would be 5. It's also the only element in our stack. Then we will push 10. When we push 10, 10 is now the top of our stack. So if we peek at the top of our stack, it will return 10. If we pop from the top of our stack, 10 will be popped. And we'll know that because afterwards, when we peek again at the top, we will see that 5 is the top of our stack. So let's test and see how we did. So first I'm going to build our code, and then we will run it. So, and here is our result. We have 1, being that the stack is empty. Then we pushed 5, so the stack is no longer empty. So when we peek, 5 is the top. When we push again and peek, 10 is the top. When we pop, 10 is removed. And when we peek again, 5 is the top. So there you go. You've successfully implemented a stack using a list from the standard template library. So now let's implement a stack using vectors. So I'm going to make a new file here, and we're going to call this stack vector.cpp. And the implementation using vectors is very similar to our list implementation. The only difference is we're going to use the vector operators instead of the list operators that we used. So what I'm going to do is I'm going to copy the stack list file and remove the implementation inside these methods and do our methods that are going to be done for our vector. So instead of including list, we are going to include vector. And instead of our private variable being a list, it's going to now be a vector. And we'll just call this v. So now let's look at our constructor method. In our earlier example, when we did a list, we didn't need to put anything in our constructor. But when we are initializing a vector, we need to reserve an amount of memory that is basically the minimum amount of memory. So we need to reserve, let's say the capacity is 30. So we request a vector capacity with at least enough to contain a certain amount of elements. So what we need to have is a capacity. So what we do is in our template, we can add int capacity. And if it's not passed, it would default to, let's say, 30. Now, when we call our constructor, we can reserve that memory. So what we can do here is v.reserve capacity. So instead of hard coding it to be 30, we're letting it so that if someone calls this stack method, they can actually change the capacity if they wanted to. So if they knew that their stack was going to hold a minimum of 100, immediately they would just reserve that memory as soon as possible. Now let's implement our clear. Remember, this is what clears our stack. A vector has the same method. It's called clear. So we just call vector.clear. When we're looking at whether or not our stack is empty, we need to know if our vector is empty. So we can return v.empty. And this lets us know whether or not the vector is empty. Very similar to our list implementation. So now we want to push an element to our stack. When we push an element to our stack, we're adding it to our vector, and we will add it to the back of our vector. Again, similar to what we did with our stack, this will be v.push back the element that we're putting in. And this will add a new element at the end of the vector our push is pretty much the same as what we did with our list. As you probably guessed it, our pop is the same as well. So we need to temporarily store our element that is at the top because we're returning it. So we go v dot back. And this would return a reference to the last element in the vector. Then we would want to remove that element from the vector. So we would call v dot pop back. And this removes the last element from the vector, basically reducing the container size by 1. And then we return our element. So our last method, we kind of have a teaser already. So if we call peak, we would just return v dot back. That is how we implement a stack using a vector. Now, if you look at this code and you compare it to our stack code, they are pretty much the same. The only difference is that we have to reserve capacity for our vector. So now that we've implemented this, let's test our code. So we compile and then we run, and we have the same output as we did before. Congratulations, you have learned what stacks are, why we use stacks, and how to implement a stack using a list and a vector from C++'s standard template library. In our next video, we are going to learn about queues. So if you like what you saw, make sure to subscribe to my channel so you can get notified for other videos, and happy learning.